Welcome back, everyone. Today we're going to talk about series, section 2, chapter 11. So, last time we talked about sequences, and we said that AI represents, AN represented the nth term of a sequence, assuming that the sequence starts from A1. And if you add up the terms of the sequence, and say starting from A1 and add it up to nth term, that creates like a finite series. So this, you can write it in a shorter way, A1 plus A2 plus A3 up to nth term. You can write this in a shorter way and write it as summation. The sigma represents summation. You probably have seen it before, of AKs, where the sub-indices start with. It starts from 1 up to, so this upper and lower sub-indice tells you starts from the first term up to the nth term. So sum of those terms of the sequences from the first to the nth term. In the case of infinite series, means if the series continuously goes on forever, then the upper bound would be infinite. Means add up all the terms of the series. In this case, you can start from k equal to 1. Say add all those AKs or AIs. A1 plus A2 plus A3, so these sub-indices will go on to infinity. So this will represent an infinite series. This is an infinite series. This is an infinite series. Okay. Now, if you look at what would be the summation of this series, what you can do is focus on smaller portions. For example, if you only look at the first term, you can show that as S1, which is the partial sum of the first term. If you look at the two terms together, A1 plus A2, that would be the sum of the first two terms. You can write it as S2. The sum of the first three terms, you can say that this is the S3, sum of the first three terms. So on and so forth, you can say the sum of the first n terms of the sequence would be basically Sn. So these Si's, so Si represents the partial sum of the sum of the uh, I is terms of the sequence. So A1 to AI, or in this case from S1 to Sn, represents the sum of the first nth term of the sequence. And if we look at these SIs, these SIs we can show SI or Sn, I can write it, starts from 1 to infinity. This basically is a new sequence, which is the sequence of those summations. What you can say is that if the sequence is convergent, then the summation exists and that summation will be convergent. So basically, we can say an infinite series is convergent if these partial sum converge. Otherwise, if the partial sum is not convergent, that means the series would be divergent. It's exactly the same idea that we had for sequences. You can extend it to series. But in the series, we don't look at specifically one term of this sequence. We look at the partial sum, the sum of the first nth term of that sequence to see what is the behavior. So generally speaking, if you want to find the total sum of the limit, then you look at the infinity limit of those partial sums, and that would be, in the case if it's convergent, it will be convergent to some L or S in this case, just to match the indices. So this S is the limit of those partial sums, and that is exactly the sum of the series. Okay, so here's an example just to make it more clear. Suppose that this summation of the first nth term of the sequence is given as 2n divided by Sn plus 5. What does it mean? That means if you look at A1 plus A2 plus A3 up to AN, you don't know anything about the ANs at the moment. What you know is this summation is basically 2n divided by 3n plus 5. By the way, you should be able to find out what is AIs just by doing simple subtractions. You can find out what is A1 by replacing n with 1. You'll get 2 divided by 8. And if you want to find a2, then you should say this would be s2 minus, okay, maybe I should write it this way. s2, this is the same as s1. s2 would be a1 plus a2, sum of the first two terms, which we already know what is a1. a1 is 2 over 8, so 2 over 8 plus a2 must equal to, replacing n with 4 divided by 12 plus 5. Sorry, 6 plus 5, which is 11. Okay, so you can figure out what is a2 and so on. But that's not the case that I wanna point out at this moment. What I want to point out is if, well, let me erase these. If we know the partial sum, which means if you know Sn, and given Sn as 2n divided by 3n plus 5, what can we say about the infinite limit? The infinite sum. That basically means find out what is Sn sequence converges to, as n from 1 to infinity. What is this sequence converges to, as, maybe I should say, question mark, as n approaches to infinity. Or you can look at it as find out what is limit n approaches to infinity of Sn. This is exactly the same as summation of a k's k from 1 to infinity. That's exactly the same. And we've learned how to calculate the limit of Sn's from last section. If Sn's are basically these sequence, so Sn is basically the sequence of 2n divided by 3n plus 5. So what would be the limit? This would be limit Sn n approaching to infinity is limit 2n divided by 3n plus 5. N approaches to infinity. You can use Hopital rule. You can divide every term by n. Either way is fine. I'm going to divide by n. 2n, 3n divided by n, 5 divided by n, as n approaches to infinity. So now this term would be approaching to 0. This approaches to 2, and here would be 3. Right, the n's will cancel. So what we have is finally 2 sides. So what I can say is this summation is basically 2 sides. Okay, nothing too complicated. It tells you about the convergence. So I can say this series AKs will be converged. Again, the AKs are not given. It's the partial sum is given. You can always figure out the AKs generally by writing the partial sums down and breaking it down. Okay, a specific case of series is the geometric series. In this case, if you look at the series when there's a common ratio, starting with, for example, if you have a sequence, let's think about the sequence for the moment, sequence 2, 6, 18, and so on, which means that every step I'm multiplying a new constant. Here I multiply 3, then I multiply the same constant, 3, multiply by the same constant. This is a geometric series. So what you get is the next term would be basically the previous term multiplied by 3, or you can say I start with the first term, then the next term would be a times a constant, another constant, the same constant again, same constant again, and so on. So if we're looking at this sequence, this is basically a geometric sequence. So the summation of this geometric sequence is what we're looking for from 1 to infinity. So what we need to first find is the partial sum of the sequence. So I need to find out what is Sn, which is basically sum of the first nth term of the sequence. So A is the first term, AR is the second term, and I can say AR to the n minus 1 is the nth term of the sequence. So how do I find the summation? Is basically there's a trick If you multiply an r to both sides of this sequence, so if I multiply an r to both sides, what do I get is rsn. And the first term would be a times r, the second term would be ar squared, and so on. The last one would be ar. Okay, let me write one extra term, arn. Okay, let me here add one more term, n minus 2, n minus 1. So these are the nth term of the sequence adding up together. So now subtract the bottom one from the top one. What do you get if I do that? If I subtract the bottom from the top, what do I get is, or the top from bottom, either way. So what I'm going to do is I'll subtract the top from the bottom. I get 1 minus r Sn. On the right side, what happens is these two terms will cancel out each other, top from bottom. The next term will cancel out with ar squared. The next one will cancel out with this one, and so on. Arn will cancel out with this. Arn minus 2 will cancel out with that. So basically, what is left is a minus ar to the n. Or you can factor out an a and say 1 minus ar to the n. So now I can find out what is Sn. So Sn simply is a 1 minus r to the n divided by 1 minus r. So this is the sum of the first nth term of a geometric series. So if they write a geometric series, you can say, okay, the sum of the first term of ar k to the minus 1, here k from 1 to n, this is exactly a 1 minus r to the n divided by, sorry about that, 1 minus r. Okay, so what can we say about the convergence of the geometric series? This is maybe the main thing that I wanted to talk about. What we can say is, let's figure out what is the limit of that Sn as n approaches to infinity, which is basically limit a times a is a constant, 1 minus r to the n, divided by 1 minus r. Okay, n approaches to infinity. First of all, if r is equal to 1, then you would have a constant sequence. So you would have a, and so on. And if you add up all these till infinity, the only way that summation would be convergent is a is exactly 0. Otherwise, if you add 1, for example, 1 to infinity, then this would be infinite. So you would have a divergent sequence. So our assumption is, in the case of r equal to 1, you have to say it is not convergent. Unless a is 0, which means you have a 0 sequence, basically. And so I can say divergent. Okay, what if r is not equal to 1? So the denominator wouldn't be 0. So let's say, what if r is less than 1? What happens? If r is less than 1, then this term, if you remember from the last section, if r is less than 1, r to the n would approach 0 as n approaches to infinity. This will approach 0 as n approaches to infinity. So what do you get as the limit? So the limit of Sn as n approaches to infinity would be exactly a divided by 1 minus r, because you would have 1 minus 0 in the numerator multiply. So in that case, we have a convergent sequence, and this is the limit. And if r is greater than 1, by the way, this is, maybe I should say absolute value. In case of negative, you still follow the same structure. Absolute value of r. Yet if absolute value of r is greater than 1, then what happened is the numerator would be approaching infinity. In that case, this term will be infinity if r is greater. So you have infinity times a constant divided by another constant. So the limit would be infinite, or you would have a divergent sequence. Okay, so we say the summation for geometric sequence exists only if the common ratio that you multiply at every step is less than 1. Otherwise, you would have a divergent sequence. So, for example, this is a divergent sequence. If you write the summation, you would have the divergence here. If you write 2 plus 6 plus 18 and so on, then you would have a divergence here. Okay, so now let's try it on this example. Find the sum of the geometric series. There are 2 of them. So let me shift this up a bit. We have space. Okay. Okay, so let's focus on maybe A, here, A, this guy, and B, this one. Let's focus on A first. You have this sequence. Think about this series, not the sequence. First, the first term is A, in this case is 5, it's the first term. And what is the ratio? What do you multiply at every step? So if this is the first, then what you multiply to get the next term is basically you multiply negative 2 over 3. To check that if it's really the ratio, you should multiply that to 10 thirds to see if you'll get times negative 2 thirds. Do I get 20 over 9? Yes, I get. And if I multiply by again negative 2 over third, do I get the next term? And so on and so forth. And you notice that it is a geometric series. And you can write it as summation 5 times negative 2 thirds to the power k minus 1, so like k minus 1, k from 1 to infinity. This is basically what the question is. And it'll be exactly that summation. And how do you find the summation? You look at the common ratio. If the common ratio in this case, absolute value of r, which is 2 thirds, is less than 1, so this series is convergent, and the result must be a times 1 minus r to the n, which basically would be a divided by 1 minus r. This is the simplified version already here. So I can say the summation would be 5 divided by 1 minus negative 2 thirds. And that is 5 divided by 5 thirds, simply 3. So if you add up this sequence, the terms of the sequence here, you'll get basically a 3. Okay, how about part B? Part B, we have 17 over 10 to the power 2 plus 17 over 10 to the power 4, and so on. I should write one more term just to make it clear. And you can think about this. This is quite easy to see. You'll have 17 over 10 to the power 2 multiplied by what would be the next term? The common ratio is 1 over 10 squared. That is the common ratio. And the power k minus 1. I write it this way just to show you that this is a, and the common ratio would be whatever you multiply to get the next term. So you multiply 1 over 10 squared. That is the common ratio. Okay, so what is the summation? Okay, from 1 to infinity. Sometimes they use subindices n. For me, I normally use k. It's not any different. So it would be again, since the common ratio is less than 1, you can do this 17 over 10 squared divided by 1 minus 1 over 10 squared. And this is simply 17 over 99. The 10 squared can cancel out. You would have 17 over 99. So this tells you actually something else too. I wanted to mention it. That's why I wrote this example. If you think about this, what you have is the first number is 0.17. The second number is 0.0017. The third number is 0.0017, and so on. So what you get basically is the result is 0.17, 17, 17, and so on. Or you can write it as 0.17 repeat itself. And what we showed that is this number is exactly the same as 17 over 99 in terms of fraction. You can use your calculator, divide this into your calculator to see if that's exactly the same number that you have or not. If you type this in the calculator, you should get 0.17, 0.17, and so on, 1717, and so on. Okay, here another example. So show that this series is convergent. This series is not really a geometric series, but you should be able to show that it's convergent by doing a simple trick. And the trick is using a telescopic behavior. And what do I mean by that is let's look at the series and see what can we get through this fraction. So first the hint is if you look at this fraction 1 over k plus 1, that is basically the difference of 1 over k minus 1 over k plus 1. And just to make sure that this is a true statement, let's do common denominator. If you multiply the first fraction by k plus 1 in the denominator and numerator, what we get is 1k plus 1, and here you get k plus 1 minus 1 over k plus 1. If I multiply k here, times k, times k. What do I get is I will get the same denominator for both of them, k plus 1, and the numerator for the first one is k plus 1, for the second one is k. And these two will cancel out and you will get exactly what you have. So now if we look at this series, summation k from 1 to infinity of 1 over k plus 1, you can think about this as summation k from 1 to infinity of 1 over k minus 1 over k plus 1. But that doesn't really give you that much unless you think about it as this way. Let's write out a couple of terms of the sequence so you can see it clearer. If I have let k equal to 1, what we have is the first term of this series, 1 over 1 minus 1 half. Replacing k with 1. Plus, this is the first term of the series. Second term would be, if you replace k with 2, you'll get 1 half minus 1 third. If you replace k with 3, you get 1 third minus 1 fourth. And now you see a pattern. What happens is this is exactly the opposite of that. This is the opposite of that, and so on. So what happens at the end is basically every term will cancel out except the first and last term. Except, so let me write this, the first and the last term, wherever we stop. So since we're dealing with the infinite series, what do I need to focus on is the partial sum first. So I say, okay, what would be Sn? Which is the sum of the first nth term of the sequence, 1 over k plus 1, k from 1 to n. And as I mentioned above, it would be the first term minus, okay, so here 1 over 1 minus 1 half plus 1 half minus 1 third, just to make sure. Dot dot dot. The last term is 1 over n minus 1 over n plus 1. And everything in this sequence will cancel out. This will cancel out with that, this will cancel out with the next one, and every term cancel out, this will cancel out with the prior one. There will be negative 1 over n. So all these terms in the middle will cancel out. What is left is only the first term, which is 1 over 1, simply 1, minus the last term, n over 1 over n plus 1. This is called a telescopic series, basically canceling out the next term. So what I found is basically Sn. So what would be the summation 1 over k plus 1? It would be figure out what is this limit. It is the same as the limit Sn, which is 1 minus 1 over n plus 1 as n approaches to infinity. And what is that limit? That limit is if you let n approaches to infinity, this term approaches to 0, the denominator would be infinite, so what you get is simply 1 minus 0, simply. So if you have a telescopic series, this is basically what you do. You set up the format just to figure out what is the Sn, then calculate the limit, and that gives you the summation. On the other side, the harmonic series is divergent. So just to understand what is a harmonic series is simply the series in the form of in the form of 1 over n. And n starts from 1, or it could start from anywhere else actually. So, but in this case, if we start with 1, what you have is 1 plus 1 half plus 1/3 plus 1/4, and so on. Let me write one more: 1/5, 1/6. Okay, we claim that this series is divergent. You can prove this by doing the SNs, but I don't want to write the SN because you have to solve inequalities. What I'm going to do is I'm going to show you you can't actually exactly figure out what is SN. So what I'm going to show you is that you always can make this to be larger than any number that you want. Here we have a 1, we have 1 half. Sum of these two numbers is always greater than 1 half. This is always greater than 1 half. So here, what I've created is another 1. Okay, so these two will add up with 1 again. If you write 1/5, 1/6, 1/7 plus 1/8, this summation would be again greater than 1 half. This would be again greater than 1 half. So this at least would be 1 plus 1 plus 1 half. And if I continue this, I can say the next terms up to 1 over 16 would be greater than 1 half. And the sum of these two would be at least 3. So any numbers that I consider, so this is 1 plus 1 plus 1 would be 3. Any number that I consider as the limit of this series, I can always surpass that by just finding out where do I need to stop for the Sn. So the Sn's, which is the sum of the first nth term of the sequence, always can surpass any large number. So this, let's say if I go from 1 over 17 to 1 over 32, this would be again greater than 1 half. And so on. 133 to 164 is greater than 1 half, and so on. You can add those numbers. You can create another one, and that would be larger than 4, larger than 5. And continuously you can show that this summation would be divergent. Okay, that is not really a clear proof, but it shows you an idea of the construction of this divergent behavior. On the other side, if you have a convergent series, then definitely the end limit of ANs must be, if you have an AN and you want to find out the summation of those ANs, this summation would be convergent if and only if the limit of AN as n approaches to infinity is 0. It means the ANs must approach 0, otherwise you will have that divergent series. So if the limit of the ANs is not 0, or if it doesn't exist, the limit, then in that case you would have a divergent series. Okay. Here, example, check for the divergence of this sequence, this series, sorry. So this is Sn. Sn is given n squared divided by 5n squared plus 4. How do we check for the divergence of the series? Is basically you can figure out the limit. What would be the limit? As n approaches to infinity, you can calculate that this is 1 divided by 5. So I would have a convergent sequence. Oh, sorry. I thought this is Sn. Not Sn is not given. This is An. An is given, not Sn. N squared. There it is. So we don't have Sn. We have An. This is the An. Okay, the nth term of the sequence, and we want to find out the convergence or the divergence of the infinite series. So what we can say is, let's figure out what is the behavior of an. So let's figure out what is the behavior of an as n approaches to infinity. It would be limit an would be n squared divided by 5n squared plus 4. Again, you can divide everything by n squared, simplify, and you will see that this is simply 1/5. That means this sequence, let me write a couple of terms of the sequence. So here, just from that theorem, that if the limit an's are not 0, then I can say I have a divergent series. I don't have a divergent sequence, I have a divergent series. That means the summation is divergent. It's not that the sequence is divergent. Okay, so just to make sure that you see this divergent, I want to show you a couple of terms of the sequence. So this summation is basically 1. If you replace n with 1, you have 1 divided by 9. If you replace n with 2, you would have 4 divided by 2, 20, 24, and 3, 9 divided by 70 something, 70, 25, sorry, 9 times 45, 45 and 4, 49, and so on. And as the numbers are getting larger, what you would get is a number closer to 1/5. And all the next numbers would be closer and closer to 1/5. Not exactly 1/5, but they'll be closer and closer to 1/5. So what you're adding is a bunch of 1/5, 1/5, and 1/5. So this summation will be actually approaching infinity. That's why we have a divergence here. Because these numbers will not be going approaching to 0. They will be increasing. So the summation will be increasing and approaching to infinity. Okay, so it is important that the an's approach 0, otherwise you'll have a divergent series. Okay. Okay, so now let's focus on this last theorem, which is a consequence, basically, existence of limit. So if you have two convergent series, that means the limit of S and both exist, then what you can say actually is that if you multiply a constant to that limit, to that series, then what you have is convergent series. So if you multiply C to the sequence ANs, then the summation of CANs is still convergent, and the limit would be basically C times the summation of ANs, because it's a constant. It doesn't affect anything. If you have to add up the two sequences, you can calculate the sum of each sequence separately, and sum of each series separately, and add them up, and same with the difference. Just to make it clear, let's look at the summation here below. I have two separate series you can look at. So and I want to find out if the sum exists and what would be the sum. So here, what I'm going to focus on is the two separate series, summation of 3 divided by n plus 1, n from 1 to, maybe I should go back to k just to be consistent. Let me change these to k, 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 and k. Okay, so here you have k plus 1, k from 1 to infinity. I want to figure out what this is. Then I will figure out what is the summation of k from 1 to infinity of 1 over 2k, 2 to the k, and add up these two, because the summation is basically becomes the sum of these two. And this would be only true if each one are convergent series. Okay, so the first one is, we've already talked about it. Actually, we've talked about both of these two, but just to remind you of it, summation, the nth term of this series, the partial sum of this series, is the same as sum of 3 divided by k. Since there's a constant there, I can put the constant outside too, just to make sure that you see it. 3 1 over k plus 1, k from 1 to n. This is the same as 3, summation of 1 over k, if you remember, 1 minus 1 over k plus 1. I just talked about that earlier a bit. And I said this is a telescopic series, which means you have a 3 times 1 minus 1 half plus 1 half minus 1/3 and so on. And you have 1 over n minus 1 over n plus 1. And this summation, everything would have cancelled here. This 2 will cancel out, 1/3 and the next one will cancel out. All these terms will cancel out except the first and the last term. And this was simply 3 times 1 minus 1 over n plus 1. You don't need to continuously rewrite this. I just wanted to show you that the Sn is simply 3 times 1 minus 1 over n plus 1. And so what can I say about the limit? Therefore, the limit Sn as n approaches to infinity would be limit 3 times 1 minus 1 over n plus 1 as n approaches to infinity, and that is simply 3 times 1 minus 0, which is 3. So I figured out what this summation approaches to. It approaches to 3. So the sum would basically be 3. And how about the other summation? Let me choose a different color. So if you want to find out what is the summation of 1 over 2 to the power k, k from 1 to n, so the first nth term of this sequence is the same as 1 plus 1 half plus 1/4 and dot 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 up to 1 over 2 to the k. Sorry, this is starts from 1 half, not 1. 1 half plus 1/4 plus. So what kind of sequence is this? Is a geometric sequence where the first term is 1 half. So a, maybe I should mention, a is 1 half. And what is the ratio? The common ratio is, what do I multiply to 1 half to get 1/4? I multiply a 1 half. So what do I need? So I can say, actually I can say this, let me just mention that this is Sn. If you remember, we calculated this was a1 minus r to the n divided by 1 minus r. But we already calculated the limit of Sn and said limit Sn as n approaches to infinity, in the case when r is less than 1, absolute value of r was less than 1, this was a divided by 1 minus r, which in our case it would be 1 half divided by 1 minus 1 half. And that's 1 half over 1 half, simply 1. Okay, so we figure out that this summation is simply 1. So originally we can answer our question, what is this summation? The summation of 3 plus 1 should be 4. If it was subtraction, you would subtract them together. In this case it's addition, you add those two. Just because the limits for both of them exist, you can say simply this becomes 3 plus 1, which is 4. Okay, so this is where I am going to stop, but every other case you should do the same thing. You don't always need to write down every term of the sequence, but this just gives you an idea how the sequences are added. Are they going to be telescopic sequence, geometric sequence? After a couple of examples, you will notice similarities. Okay, so let's stop here.